so we've said why A equals QR is useful. If we are given an A equals QR factorization, any projection problem involving A becomes simplified, and any least squares problem involving A is simplified. So the natural question to ask is, well, what if I don't have that information? What if I have some matrix A that I'm interested in, but I don't have a QR factorization of that matrix? So how do we find this factorization? Well, remember that in a QR factorization, the columns of Q form an orthonormal basis of the column space of A. So that means that the columns of Q are all unit vectors, and they're all mutually orthogonal. And if we looked at the span of those columns, we would get the same thing as the span of the columns of A. So this is where our idea starts. Let's start by trying to find the information in the columns of Q, and then maybe we can use that information to find the entries in R. So let's start by finding an orthonormal basis of the column space of our matrix. So to really flesh this idea out, I want to look at a prototype where we're looking at an example where the dimension of maybe any space we're working with is 2. So let's say that we're starting with a basis v1, v2 for a vector space V. So consequently, the dimension of that space is 2. And let's ask the question of whether or not it's possible to convert that basis into an orthonormal basis, q1, q2, of that vector space. So the idea here is that maybe we start with two basis vectors for a space, v1 and v2. And maybe the issue here is that v1 and v2 maybe both don't have length 1. And as illustrated in this diagram, maybe that they're not even orthogonal to one another. So how are we going to take this information and get an orthonormal basis from it? Well, the idea is going to come in 2 phases. The first thing we're going to do is we're going to construct new vectors w1 and w2 that are orthogonal to one another in this space, but aren't necessarily unit vectors. Then we're going to take those non-unit vectors and normalize. So here's how the procedure goes. We're going to start our algorithm by defining a new vector w1, and the formula for w1 is the simplest formula of the whole algorithm. We just set w1 equal to the first basis vector v1 that we start with. So w1 is just straight up equal to v1. Now the question is, where are we going to get our w2? So we clearly can't choose w2 just equals v2, because as illustrated in this figure, w1 and v2 are not orthogonal vectors. So here's what we can do. Let's say that we just tried to create an orthogonal vector from this figure. Maybe one thing we could do is we could take the tip of v2 and drop down to the vector w1. This is exactly the idea behind projections. So let's look at exactly that vector. So let's define a vector w2 by this figure. What we're doing is we're dropping an orthogonal from the tip of v2 down to the vector w1. The idea is that the tip to this intersection here is the projection of v2 onto w1. And if we look at this difference vector, we're defining a vector w2 that's orthogonal to w1. So the formula for w2 here should be we start with v2 and then subtract off the projection of v2 onto w1. So now we've taken the information of v1 and v2 and we've converted it into information w1, w2, where the vectors w1 and w2 are orthogonal vectors. Now remember, from our perspective, vectors don't inherently have a specified location, so we can take this w2 in our diagram and translate it back to where w1 emanated from. So now we have a nice diagram. We've taken the basis v1 and v2, and we've converted it to a new basis, w1, w2. And w1 and w2 here are clearly orthogonal vectors. Now, this is not necessarily an orthonormal basis because w1 and w2 don't necessarily have unit length. We can fix this problem, though, by normalizing each of those vectors. So how do we take w1 and convert it to a unit vector? Well, we can look at the unit vector that points in its direction, which is exactly the idea behind normalization. So we define our first Q1 in our orthonormal basis as W1 divided by its own length. And we do the same thing to construct the vector Q2. Q2 is going to be the unit vector that points in the same direction of W2. And its formula, therefore, should be Q2 equals W2 divided by its own length. So at the end of this procedure, we end up with a new basis, Q1, Q2, for the vector space in question. And this new basis is nice to work with because these are both unit vectors that are orthogonal to one another. So this is the idea behind what's called the Gram-Schmidt algorithm, which is an algorithm that will work if we start with any number of basis vectors. Here, we're looking at the figure for dimension equaling 2. The full Gram-Schmidt algorithm will work for any dimension. So let's walk through the technical statement of the entire Gram-Schmidt algorithm. The idea is inspired by the prototype from the previous slide, but when the dimension is bigger, there are more W's to calculate. So let's say that we start with a basis V1 through Vd of a vector subspace V of Rn. So consequently, the dimension of V is equal to D. So the algorithm is going to come in two phases. First, we're going to calculate W's, then we will calculate Q's. So, just like on the previous slide, the formula for the first W is W1 equals the first V, so W1 equals V1. Then to calculate the second W, we use the idea from the previous slide. The second W is the second V, but we need to subtract off the projection of that V, so V2, onto the W that we just calculated, W1. So W2 is V2 minus the projection of V2 onto W1. So if there were just two basis vectors, the algorithm would stop here as far as the W's are concerned, but since there are more V's, we need to calculate more W's. The idea is that we follow this pattern. The third W is obtained by plucking out the third V from the list. Then we subtract its projection onto the first W we calculated. Then there's one more step, which involves subtracting off the projection of that third V onto the second W we calculated. So at every stage of creating a W, we pluck out the next V in the list, and then we subtract all of its projections onto the previous W's we calculated. So this pattern continues until we get to the last V in the list. So the last W we calculate is W sub D. W sub D is obtained by plucking out the last V, V sub D, from the list. And then we subtract off each of its projections onto all of the previous W's we've calculated. So the dth W here is V sub D minus the projection of V sub D onto the first W, minus the projection of V sub D onto the second W, minus the projection of V sub D onto the third W, and we keep going until we get to the subtracting off the projection of V sub D onto the second to last W that we're constructing here. So at the end of this first phase of the algorithm, we end up with a basis of V given by W1, W2, up to WD. And this list is guaranteed to be a mutually orthogonal basis of V, because by subtracting all these projections, we are forcing these W's to be orthogonal to one another. This, however, is not an orthonormal basis because each of these W's is not guaranteed to be a unit vector. We can correct for this by defining Q's to be the normalizations of these W's. So after we've calculated all of our W's, we can calculate our Q's by normalizing the W's. Q sub 1 is the normalization of W1, so W1 divided by its own length. Q sub 2 is the normalization of W2, W2 divided by its own length. Oops. Q sub 3 is the normalization of W3, and then the last Q, Q sub D, is the normalization of the dth W. After defining these Q's, we end up with an orthonormal basis of V. So Q1 and QD, Q1 up to QD, forms an orthonormal basis of the vector space V we started with. So by the end of the algorithm, we have a total of 3 different bases for the vector space. We have the basis we started with, V1 through Vd. Then we have the w's that form a basis. These w's are all orthogonal, but not necessarily unit vectors. Then by normalizing, we get our orthonormal basis, q1 through qd. Okay, so let's see this algorithm implemented. So this is the Gram-Schmidt algorithm, where the vector space we're starting with is the span of this list of 3 vectors. The first basis vector is the vector 0, 0, 1, 0. The second vector in our list is -1, 2, -2, 2. And the third vector in our list is 9, 14, -4, -2. So here V is the span of this list of 3 vectors. Since this list is a basis, we know that the dimension here is 3. So once we're done with our algorithm, we should end up constructing 3 W's and then 3 Q's. So how do we define our W's? Well, the first W is the easiest to calculate. The formula for W1 is W1 equals V1, which in this list happens to be 0, 0, 1, 0. The second W has formula given by V2, the second V in our list, and then we need to subtract off the projection of that vector, V2, onto the previous W that we calculated, which was 0, 0, 1, 0. So what does this look like? Well, the vector V2 is just the second vector in our list, -1, 2, -2, 2. And then we need to remember our formula for projections. Projection takes the form dot product of the 2 vectors. So we're dotting W1 W1 with V2. Then we divide by the dot product of W1 with itself. And then we scale that we take that scalar and scale 0, 0, 1, 0, which is W1 with that scalar. So the first term here is V2, and the second term here is the projection of V2 onto W1. After doing that arithmetic, we get a new vector, and that new vector is -1, 2, 0, 2. Now, one sanity check you can implement after each of these calculations is to verify that this vector is actually orthogonal to the previous vector. So note here, if we take the dot product of -1, 2, 0, 2 with the vector 0, 0, 1, 0, we do indeed get 0. Okay, so that's our first our second W, W sub 2. Let's calculate W sub 3. By definition, W sub 3 is the third vector in our original list, so 9, 14, -4, -2. And then we need to take that vector and subtract off its projection onto the first W we calculated, and then subtract off its projection onto the second W we calculated. So if we write down each of those terms, in total we get 3 of them. V3 is the vector 9, 14, -4, -2. To calculate the projection of V3 onto W1, we calculate the dot product of W1 with V3, then divide by the dot product of W1 with itself, and then we multiply that scalar by W1. Then for the projection of V3 onto W2, we take the dot product of W2 with V3, then we divide by the dot product of W2 with itself, and then we multiply by the vector W2. Once we have all those terms, we can do all of our arithmetic, and if we simplify, we end up with the vector 16/3 times 2, 2, 0, -1. Again, we can implement a quick sanity check here to verify that all of these vectors are actually orthogonal. The vector 2, 2, 0, -1 is certainly orthogonal to 0, 0, 1, 0. If we take a dot product, we get 0. And then 2, 2, 0, -1 is also orthogonal to W2 here. -1 times 2 is -2. 2 times 2 is 4. 0 times 0 is 0. 2 times -1 is -2. And when we sum those entries, we get 0. Okay, so now these new W's form a new basis for our vector space. And these W's are orthogonal to one another. But the basis W1, W2, W3 is not an orthonormal basis because our W's are not unit vectors here. So we can finish this Gram-Schmidt algorithm by normalizing each of the w's. So in our formulas, q1 should be equal to the normalization of w1, and the normalization of w1 for this example happens to just equal w1 because our original v1 was a unit vector. Then for q2, we should take our w2 and divide by its own length. So here, if we look at w2, its entries are -1, 2, 0, 2. If we sum the squares, we get 1 plus 4 plus 4, which is 9. The square root of 9 is 3. So we're taking our vector and we're dividing by 3. Finally, to normalize w3, we can look at the vector here 2, 2, 0, -1. The sum of the squares here are 4 plus 4 plus 1. So again, we get 9. Square root of 9 is 3. And we can divide 2, 2, 0, -1 by 3. So these q's that pop out of the algorithm form an orthonormal basis for the vector space we started with. So at the end of this calculation, we have 3 bases for our original vector space. The basis we started with, v1, v2, v3. These are not all necessarily unit vectors, and they're not necessarily orthogonal to one another. By constructing the w's, we end up with 3 new basis vectors. These vectors are all orthogonal to one another, but not necessarily unit vectors. And then, after calculating the q's, we end up with a mutually orthogonal list of unit vectors as our basis. Okay, so now the idea is that the Gram-Schmidt algorithm can be used to factor A as Q times R. So we can now use the Gram-Schmidt algorithm to calculate A equals QR. To start with, we need A to be full column rank. The first step in this procedure is to implement the Gram-Schmidt algorithm to find an orthonormal basis of the column space of our matrix. So if A has full column rank, we know that the columns of A form a basis for the column space. So we can plug those columns into the Gram-Schmidt algorithm, and out pops Q1, Q2 up to QD. Step 2, we take those Q's and put them into the columns of a matrix called capital Q. That's the Q in A equals Q times R. And finally, to find R, we have a very simple formula. R can be obtained by just taking Q transpose, which we calculated in the previous step, and multiplying by the original A. After we're done with these 3 steps, we get a QR-Factorization of A. So after these 3 steps, A is equal to Q times R. So the idea here is that the columns of Q were obtained by applying the Gram-Schmidt algorithm to the columns of A, and then R is equal to Q transpose times A. So here we have the data of the example we just did 2 slides ago. So 2 slides ago, we started with 3 vectors, 0, 0, 1, 0, -1, 2, -2, 2, and then 9, 14, -4, -2. We applied the Gram-Schmidt procedure to those 3 vectors, and we got an orthonormal basis for the span of those 3 vectors. The first Q was 0, 0, 1, 0. The second Q was -1/3, 2/3, 0, 2/3. And the third Q was 2/3, 2/3, 0, -1/3. So here we're packaging all that information into a matrix A, whose columns are the original vectors in our basis. And then Q is obtained by inserting the vectors that pop out of the Gram-Schmidt algorithm into the columns of a matrix. So now the only thing we're missing in a QR-Factorization is R, and R can be constructed by using the formula R equals Q transpose times A. So if we take Q here and transpose it, the Q originally is 4/3. When we transpose, we get a 3/4. And then when we multiply by A, we're multiplying by this 4/3. When we multiply these together, we end up with our formula for R, which is indeed upper triangular. So now the idea is that in this factorization, or in this procedure, A is equal to Q times R, where Q is this matrix and R is this matrix.